Welcome to the session on probability distributions. In the previous session, we discussed some basic concepts of probability distribution. Here, we shall discuss probability density function for a continuous random variable capital X. Let x be a continuous random variable. Then, associated with x, there is a real valued function f of x such that for any two real numbers a and b, we have probability of a less than or equal to capital X less than or equal to b is equal to integral from a to b f of x dx. A function satisfying this probability equation is called the probability density function. Probability density function PDF. In short, we use PDF. Now, there is an important theorem from the consequence of definition of probability, that is f of x is a PDF, a function f of x is a probability density function of a continuous random variable capital X if and only if f of x is greater than or equal to 0 for every value of x. And the second condition is integral minus infinity to infinity f of x dx is equal to 0. In order to verify a given function can define a PDF or not, we use these two conditions. For example, consider the function f of x is equal to 2 into e raised to minus x for x greater than 0 and 0 for x less than or equal to 0. Now, we have to check this function can define a PDF or not. Here the first condition, we have to check the first condition, f of x is 2 times e raised to minus x. Clearly, this function, that is e raised to minus x exponential function, is always greater than or equal to 0. Therefore, the given function will become, that is f of x is greater than or equal to 0 for every value of x. The value of function is 0 or 2 times e raised to minus x. The e raised to minus x cannot be negative. Therefore, f of x is greater than or equal to 0, greater than 0 in this case or equal to 0 in this case x less than or equal to 0. Therefore, the first condition holds. Now, to check the second condition, we have integral from minus infinity to infinity f of x dx is equal to, here there are two limits, x less than or equal to 0 means integral from minus infinity to 0 f of x dx plus x greater than 0 means the limit of integration is from 0 to infinity f of x dx, which is equal to, in this portion the function defined as 0. Therefore, this is equal to integral from 0 to infinity. Here f of x is 2 e raised to minus x. For x greater than 0 means x from 0 to infinity, the function is defined as 2 times e raised to minus x dx, which is equal to, on integration 2 can be taken outside, integral e raised to minus x dx is limit from 0 to infinity, which is equal to 2 times e raised to minus x divided by minus 1 between the limits 0 and infinity. Now, we use these two limits. When x tends to infinity, e raised to minus x tends to 0. Therefore, this is equal to 2 by minus 1 into 0 minus, when x equal to 0, e raised to minus x become e raised to 0, that is 1, which is therefore, this is equal to 2 by minus 1 into minus 1 is 2. Here, integral from minus infinity to infinity f of x dx is equal to 2, which is not equal to 1. That means, the second condition is not satisfied by the given function. Therefore, the given function is not a PDF. Now, if the given function is like this, f of x equal to 2 times e raised to minus 2x instead of minus x, if the function is defined as f of x equal to 2 times e raised to minus 2x, then the first condition is okay, because the exponential function is this function is greater than or equal to 0 for every x. Now, the second condition is integral from minus infinity to infinity f of x dx is we split the integral into 2, and in this case the function is 0, the first integral f of x is 0, and this integral become integral from 0 to infinity 2 times here e raised to minus 2x dx, which is equal to 2 into integral e raised to minus 2x dx, which is equal to 2 into e raised to minus 2x divided by minus 2 between the limits 0 and infinity. When x tends to infinity, e raised to minus infinity tends to 0. Therefore, this is equal to 2 divided by minus 2 means minus 1 into 0 minus, when x equal to 0, e raised to 0 is 1. Therefore, this is equal to 1. That means, the second condition of a PDF is also satisfied. Therefore, the given function f of x equal to 2 times e raised to minus 2x for x greater than 0 and 0 for x less than or equal to 0 is a PDF of a continuous random variable capital X. The next example is, we are given a PDF of a continuous random variable capital X as f of x is equal to k times 1 minus x square for 0 less than or equal to x less than or equal to 1 and 0 otherwise. We have to find the value of this constant k, find the value of k and evaluate the probability of x lying between 0.5 and 2. P of probability of 0.5 less than or equal to x less than or equal to 2. Here the given function is a PDF. Therefore, we can use the property integral from minus infinity to infinity f of x dx is equal to 1, which implies integral from, here the function is defined as k times 1 minus x square for 0 less than or equal to x less than or equal to 1, and all the other cases the function is defined as 0. Therefore, we can split this integral as minus infinity to 0 f of x dx plus 0 to 1 f of x dx plus 1 to infinity f of x dx, which is equal to, the right hand side is 1. This implies, here in this case f of x is defined as 0, and from 1 to infinity means in this case function is defined as also equal to 0. Therefore, these two integrals, first and last integrals, become 0, and this integral becomes integral from 0 to 1. Here f of x is in this range, f of x is k times 1 minus x square, k into 1 minus x square dx is equal to 1, which implies k can be taken outside of integral from 0 to 1, 1 minus x square dx is equal to 1. That is k times integral of 1 is x minus integral of x square is x cube by 3 between the limits 0 and 1 is equal to 1, gives k times upper limit is 1. Therefore, this is equal to 1 minus 1 by 3 minus of lower limit that is 0 is equal to 1, which implies k into 1 minus 1 by 3 means 3 minus 1 is 2 by 3 is equal to 1, which gives k is equal to 3 by 2. Value of k is 3 by 2. Now, we have to evaluate this probability. Note that here the function is defined as f of x equal to k times 1 minus x square if x varies from 0 to 1, including 0 and 1. We have to evaluate this probability, that is probability of x from 0.5 to 2, including 0.5 and 2. But here up to 1, from 0 to 1 the function is defined as k times 1 minus x square, but here up to 2. Therefore, the required probability can be written as p of 0.5 less than or equal to x less than or equal to 2 is equal to, by definition we can write this as the integral from 0.5 to 2 f of x dx, which is equal to integral from 0.5 to 1 f of x dx plus integral from 1 to 2 f of x dx. We have to split the limit of integration into 2, 0.5 to 1 and 1 to 2. In this case, the value of f of x is 0, because this range will become in this case otherwise case. Therefore, this is equal to integral from 0.5 to 1. Here f of x is 0.5 to 1 means which lies in this interval. Therefore, in this interval f of x is k times 1 minus x square. Therefore, for 0.5 to 1 f of x also equal to the same, that is k into 1 minus x square dx. But the value of k is 3 by 2. This is equal to 3 by 2 into integral from 0.5 to 1 minus x square dx. On integration, we get the required probability is equal to 3 by 2 into x minus x cube divided by 3 between the limits 0.5 and 1, which is equal to 3 by 2 into the upper limit is 1. Therefore, 1 minus 1 by 3 minus the lower limit is 0.5 minus 0.5 cube divided by 3. Which is equal to 3 by 2 into here 3 minus 1 by 3 is 2 by 3 minus 0.5 minus 0.5 cube is 0.125 divided by 3. On simplification, we will get this required probability as P of 0.5 less than or equal to x less than or equal to 2 as it is equal to the required probability is 0.638 approximately. Now, we define the cumulative distribution function, simply the distribution function. Cumulative distribution function, in short, this is termed as a distribution function. The distribution function is defined as capital F of x is equal to probability of x less than or equal to some particular value of x. This is the definition where capital X is a random variable which may be discrete or continuous. In discrete case, we can write this definition as, if x is discrete, the definition of distribution function is capital F of x is equal to summation f of t, where t is less than or equal to some particular value of x. And in continuous case, if x is a continuous random variable, the distribution function f of x is defined as integral from minus infinity to infinity f of x dx. It is in the continuous case. This is if x is discrete, and this is if x is continuous. In continuous case, we can say that the distribution function capital F of x is also a continuous function in the interval minus infinity and infinity, and also d by dx of, that is the first derivative of capital F of x, is equal to the corresponding PDF small f of x, where capital F of x is differentiable. If the distribution function capital F is differentiable, we have d by dx of capital F of x equal to small f of x. Small f of x means the corresponding probability density function. Now, we have examples for cumulative distribution function. We are given a probability mass function of a discrete random variable capital X as f of x is equal to 1 by 4 if x equal to 0 and 2, and f of x equal to 1 by 2 if x equal to 1 and 0 otherwise. Then we have to find the corresponding distribution function. Now, we take the first case as x less than 0. In this case, here x less than 0 means here the function is defined as for x equal to 0, here x equal to 1 and x equal to 2. Therefore, for x less than 0 means there is no value of the random variable capital X. Hence, we have capital F of x equal to probability of x less than or equal to x, which is equal to 0. Now, consider the case 0 less than or equal to x less than 1. This is the case 2. In this case, there is precisely one value of x satisfying this condition, namely x equal to 0, because 0 less than or equal to x less than 1 means x equal to 0. Therefore, in this case capital F of x, that is the CDF, cumulative distribution function, capital F of x is equal to probability of x less than or equal to x means here the precise value is probability of x equal to 0 only. That is, if x equal to 0, f of x is f of 0, that is 1 by 4. Now, consider the case 3 as 1 less than or equal to x less than 2. In this case, there are two values of the random variable capital X satisfying this condition, namely capital X equal to 0 and x equal to 1. 1 less than or equal to x less than 2. In this case, capital F of x is probability of x less than or equal to x, where this x is in between 1 and 2, including 1. Therefore, this is equal to probability of x equal to 0 or probability of x equal to 1. That is equal to p of x equal to 0 plus p of x equal to 1, that is f of 0 plus f of 1. F of 0 is here 1 by 4 and f of 1 is 1 by 2. 1 by 2 means 2 by 4, that is this is equal to 3 by 4. Now, the last case is the fourth case is in case 4 x greater than or equal to 2. Consider the case x greater than or equal to 2. All possible values of the random variable capital X satisfy this condition. Therefore, capital F of x is equal to probability of x less than or equal to x, but this x is greater than or equal to 2, including 2. The possibilities are p of x equal to 0, 1 or 2. That is equal to probability of x equal to 0 plus probability of x equal to 1 plus probability of x equal to 2, that is f of 0 plus f of 1 plus f of 2, which is equal to f of 0 is 1 by 4 plus f of 1 is 1 by 2 plus f of 2 is again 1 by 4, that is 1 by 4 plus 1 by 4 means 2 times 1 by 4, that is 1 by 2 plus 1 by 2 is equal to 1. Considering all these 4 cases, we can express the distribution function capital F of x as capital F of x is equal to 0 where x less than 0 and capital F of x equal to 1 by 4 for 0 less than or equal to x less than 1. Next is 3 by 4 for 1 less than or equal to x less than 2, and the last one is 1 for x greater than or equal to 2. This is the distribution function corresponding to this given PDF. The next example is for continuous random variable capital X, that is we are given a probability density function f of x as f of x is equal to small f of x is equal to x for 0 less than or equal to x less than 1, 2 minus x for 1 less than or equal to x less than 2 and 0 otherwise. Here we take the first case as x less than 0. In this case, f of x is defined as, here the random variable capital X is continuous. Therefore, we use integral from minus infinity to x f of x dx. This is equal to integral from minus infinity to x, where x is less than 0. If x less than 0 means which will become in this case, otherwise case. In this case, f of x is 0, therefore, 0 dx equal to 0. The second case is, consider the case 2 as 0 less than or equal to x less than 1. In this case, capital F of x is equal to integral from minus infinity to x f of x dx, where this x is in between 0 and 1, including 0, which is equal to integral from minus infinity to 0 f of x dx plus integral from 0 to x, where x is in between 0 and 1. We can split this integral like this, f of x dx, which is equal to minus infinity to 0 means x is less than 0, in which case f of x is 0. Therefore, this is 0 plus 0 to a number lying between 0 and 1 means f of x will become, in this case, 0 to a number lying between 0 and 1 means the corresponding range will become in this case. Therefore, the function value is f of x equal to x, 0 to x, f of x is x dx. On integration, we will get x square by 2 between the limits 0 and x. The upper limit is x, x for x means x square by 2 minus 0. The third case is 1 less than or equal to x less than 2. In this case, capital F of x is equal to integral from minus infinity to a number which lying between 1 and 2 f of x dx, which is equal to integral from minus infinity to 0. This number is lying between 1 and 2, means this limit of integration can be split into integral from minus infinity to 0 f of x dx plus integral from 0 to 1 f of x dx plus integral from 1 to a number lying between 0 and 2, that is integral from 1 to x 2 minus x dx. This is equal to, in this range f of x is 0. Here integral from 0 to 1 f of x dx means f of x is x, integral from 0 to 1 f of x is x itself in this range, plus here f of x is 2 minus x, integral from 1 to x 2 minus x dx, which is equal to x square by 2 between the limits 0 and 1. This is 2x minus x square by 2 between the limits 1 and x. That is equal to minus 1 plus 2x minus x square by 2. Applying the limit, and on simplification we will get the capital F of x as minus 1 plus 2x minus x square by 2. Now, the last case is x greater than or equal to 2. In this case, capital F of x is equal to minus infinity to a number which is greater than or equal to 2 f of x dx. This is equal to integral from minus infinity to 0 f of x dx plus integral from 0 to 1 f of x dx plus integral from 1 to 2 f of x dx plus integral from 2 to x, where x is greater than or equal to 2 f of x dx. Is equal to, in this case function is 0. Here integral from 0 to 1 f of x dx is this one, that is integral from 0 to 1. In this range 0 to 1 function value is x dx plus if x lying between 1 and 2, the function value is 2 minus x, integral from 1 to 2 minus x dx. In this case x greater than 2 means this will become 0, f of x is 0. Therefore, this is equal to x square by 2 plus 2x minus x square by 2. Here x square by 2 is in between 0 and 1, 2x minus x square by 2 is from 1 to 2. Apply the limits and simplify, we will get this as 1. That is in this case capital F of x is 1. Considering all the cases together, we will write the corresponding distribution function capital F of x as f of x is equal to 0 for x less than 0, x square by 2 for 0 less than or equal to x less than 1, minus 1 plus 2x minus x square by 2 for 1 less than or equal to x less than 2, and 0 for x greater than or equal to 2. This is the corresponding distribution function of the given function, given PDF. Now, let me conclude this session. In this session, we discussed the probability density function and the cumulative distribution function of a discrete random variable and continuous random variable capital X. Thank you for listening the class. Have a nice day.